is chapter 5-1, perpendicular bisectors. Please copy your codes. To begin, we need to recall something that we've taught in one of the last chapters, and that's a segment bisector. If we clearly remember, a segment bisector is a point, line, ray, or another segment that will evenly divide a line segment in half. So, for example, if I take this green line out here and this one here, I have line segment AB being bisected by point Z. When I say that point Z bisects a line segment AB, that means that point Z divides the line segment AB exactly in half. So if we show the congruent symbols here, we know that AZ is congruent to BZ because it has a segment bisector by the name of point Z. Well, we recall that bisector, the key word, bisector means in half. We should be able to determine what a perpendicular bisector is. First of all, if we remember or recall what perpendicular means, that's when I have two lines or two rays, and if they intersect, where they intersect, it will form 90-degree angles. So 90-degree angle bisectors. Okay? Looking at that again, the word perpendicular simply means that 90-degree angles will be formed. And we need to recall that the word bisector means a line or ray or segment will divide another line exactly in half. What will that look like? If I have here line segment, I'm going to back this up just a little bit so that you can see this a little cleaner. If I have line segment AB here, and I say that I have a perpendicular bisector line CP, when I say perpendicular bisector, that means that the line CP is going, the way it bisects will divide this line AB and form two right angles. In this case, it will be 4 because these will be 90 degrees as well. But because it's perpendicular, it's straight vertically, well, I want to say the word vertically, but this is horizontal. This will be vertically and form two 90-degree angles because it's perpendicular. And the word bisector means that I am dividing the line in half. So AP is congruent to BP because the perpendicular bisector is going to divide line segment AB in half and at the same time cause it to form 90-degree angles, therefore making this a perpendicular bisector. The perpendicular bisector again is line CP. It divides line segment AB exactly in half so that AP is congruent to BP, and at the same time it causes to form two 90-degree angles. All right? And because point P, if I'm looking carefully here, point P, this center point from the line CP, just looking at the one point P, because point P is exactly in the middle of segment AB, that means that point P is what we call equidistant. Think of the word equal. What does equal mean? Equal mean equal distance. So point P is equidistant, meaning that the distance from P to A is exactly the same length or distance from P to B. So, again, point P is exactly the same distance away from point A as it is from point B. Some theorems from chapter 5 and 5.1. Let's look at the perpendicular bisector theorem. That means if a point is on the perpendicular bisector of a segment, then it is equidistant from its endpoints of a segment. What do you mean? Okay? Again, if a point is on a perpendicular bisector, i.e. point C, Point C is on the perpendicular bisector. How do I know it's CP is a perpendicular bisector? Because CP divides line segment exactly in half, and I know that because AP is congruent to BP. And at the same time, where CP intersects AB, it causes it to form two 90-degree angles, which means I really should have four because these bottom ones would be 90 degrees as well. Because this is the case, point C that's on the perpendicular bisector CP, any segment I draw from point C to the endpoints will be congruent. So what that means is if I draw a segment from C to A and then C to B, because CP is a perpendicular bisector, that means that AC is congruent to BC. I can take any point. Let's say I have a brand new point, and I have point, I will call this one point, I'll call that Z. Because point Z lies on the perpendicular bisector CP, if I drew a new line from point Z over to A or Z over to B, that also means that ZA is congruent to ZB. ZA is congruent to ZB because point C lies on the perpendicular bisectors exactly in half. Doesn't matter where I place the point on the perpendicular bisector. If I connect it to the two endpoints, the two new segments will be congruent. So finally, if I chose to do, I call this point down here L. And I connect L to B, and then if they were straight lines, I'm just drawing freehand, but if they were straight lines, LA would be congruent to LB. Because point L lies on the perpendicular bisector. Now point L we're laying over here, like this here, and I connect it over to A and then to B. LA would not be congruent to LB because point L would not be on the perpendicular bisector. Okay, and as stated, as I already stated, CA is equal to CB, and notice there's no hat. Remember when I put the hat, that means I use congruent. There's no hat there. That means I want the numerical value. That means the numerical value of CA is equal to the numerical value of CB. Okay? Some more information that I stated verbally. It is now written. If CP is the perpendicular bisector of line segment AB, then that automatically means that CA is going to be equal to the same length as CB. Okay? So it doesn't matter if I draw two new lines that connect from the perpendicular segment to point P, points A or B, the two segments will be congruent. And that's just explaining how I drew a new point at Z and connected from ZA to ZB. ZA is congruent to ZB. And again, this is another example where I drew point L. LA is congruent to LB. It doesn't matter where I draw the new point, as long as it's on a perpendicular bisector, will be congruent. The two segments will be congruent. All right, and moving further is the converse, the opposite. Okay, if a point is equidistant from the endpoints of a segment, then it's perpendicular. Then it is on the perpendicular bisector. So, on the converse, if a point is equidistant, point P in this case is equidistant from point A and point B. Because point P is equidistant, and I know it's equidistant because I see the two markers that say that AP is congruent to BP. Because the point P is equidistant to the two endpoints, that automatically means that if there's a line that's perpendicular, or the perpendicular bisector, that automatically means that point P has to lie on the perpendicular bisector. Okay? And if that's the case, when I look at this here, let's say I call this line CD. Here's my new line. Because CD is a perpendicular bisector, if I take a line and draw it out to point B from D, and I draw another line segment from point D to point A, remember AD is going to be congruent to BD. And that also means that D is on line CP. Okay. Last bit of information, if DA is equal to, as I stated, DB, that automatically means that point D lies on the perpendicular bisector, just like P and C. Okay, so really, for this particular converse, okay, if a point is equal distance, and I know that here, if I'm looking at this point and I say that this is equal distance even on an angle, because point D is equal distance from AD to BD, I know it lies on the perpendicular bisector. So if I put a new point here, any point, and I call that R, like R. I draw R to A and then R to B. If these 2 points are congruent, I'll make that 3. If RA is congruent to RB, that automatically means that point R is on the perpendicular bisector. That's what the converse means. And finally, last 2 theorems deal with angle bisecting. And this is theorem 5.3 with an angle bisector theorem. If a point is on the bisector of an angle, then it's equal distance from the 2 side angles. Okay? So I have angle BAC. And if a point is on the bisector, I'm saying the bisector is ray AD. If ray AD divides angle BAC exactly in half, then that means that this going to form here a perpendicular bisector. Okay, from A to from D to C is going to be a perpendicular, and from D to B will be also perpendicular. Okay, and I know it's equal distance. That means that BD is congruent to CD. BD is congruent to CD. Okay. I could do another point on the ray. If I call this point R, and I drew the perpendicular lines here. If they were perpendicular, that automatically means, and I would need some names here, I will call this M and V. That means that VR is going to be the same length as MR. And the converse is just the opposite statement. And before I get to the converse, we have DB, as I stated, is equal to DC. If the measure of angle BAD is equal to, so the measure of angle BAD, this angle here, is equal to the measure of CAD, the second lower half, then that automatically means that DB is equal to DC. So the first angle is equal to the second. Okay, these 2 segments, BD and CD, are equal. And the converse is just the opposite. Now if I say that the 2 segments, the converse is just a segment. So if I say that the 2 segments, DB and DC, are congruent on an angle bisector, then that automatically means that the 2 angles will be congruent. Angle BAD will automatically be equal to the measure of CAD. So it's just the opposite here. So this time I said that the 2 segments are congruent on an angle bisector, then that means automatically that the 2 angles will be congruent. And on the first one, the original one, instead of saying the segments, I said if the angle, on this first one, I said if the angles BAD are congruent to CAD, then that means that the 2 bisected segments will be congruent. Now on this one, I'm automatically telling you that if the 2 segments, BD and CD, are congruent, then that automatically means that the angles BAD and CAD are congruent.